All right, so we left off last time talking about establishing identities, and we actually did 5 of them, and we're going to do a couple more today, and then you guys are going to practice on some on your own. So, whoops, let's try that again. All right, so this one looks a little different than some of the ones we were dealing with yesterday. We've got a fraction on both sides, and perhaps even when you look at it, you're looking at it and thinking both sides look a little complicated. I mean, they don't look real clean. Like last time when we were dealing with some of them, one side equaled cotangent. It was nice and clean and clearly the simpler side. And this one doesn't sort of have that feel to it, does it? But we can deal with it, and we can work with either side. Preferences, what would you like to change, or how would you like to do the problem? If you were trying to show that these two sides are the same, what might you try? Do you have an idea, Landon?
Make the right side sine and cosine.
I think that's a good plan. We notice on the left-hand side everything's in sine and cosines, and I can do that pretty quickly with the cotangent because there's only one term to change over there, right? So what would I actually end up getting for cotangent? What is cotangent in terms of sines and cosines? Cosine over sine. That one's the cosine of theta over sine of theta. And let me reiterate, every time you write sine, cosine, or any of the other trig functions, they need to have the angle with them. So whatever the angle starts with in the problem, it continues. All right, so now I've got a complicated looking fraction on the right-hand side because I've got a fraction within a fraction. And you learned in algebra how you deal with that. What do? That's one way of doing it, Michael. Does anybody learn anything different? You can only flip it and multiply if the whole denominator is one fraction, and it isn't right now, which would mean you could do common denominators like Michael suggested. Any other thoughts? Okay, let me show you an easier way to do it than actually getting the common denominators. Michael, if we were to get common denominators, what would it be? It'd be sine, right? If I were to if I looked at the bottom of the fraction currently and I wanted to combine that into one fraction, I would use sine. And then we could do like Caitlin suggested and we could flip it, right? I'm going to suggest that instead of actually finding common denominators, we use what the common denominator would be and we multiply by it. If I multiply by that on the denominator, that is the 1 minus cosine theta over sine theta, I have to do it to the numerator as well, where simply the 1 is. So on top, nicely, I get sine theta, which is awfully friendly because that's what it actually already is on the left-hand side of my equation, right? Keeping the goal in mind, where am I headed? And then over here on the denominator part of it, I have to distribute, right? So each of those pieces have to have sine multiplied by it. So what is 1 times sine? Sine, just like it was in the numerator. And what happens to the cosine theta over sine theta when it's multiplied by sine?
The signs cancel.
The signs cancel, right? And I'm left with cosine, and it's a negative. And lo and behold, that's actually exactly what I wanted it to be, isn't it? Okay, so if you don't like what I just did, that's fine. You can actually find the common denominators and flip it. It's perfectly fine with me to do that. This just kind of sort of cuts the middleman out. It does it in about 1 step instead of 2. So that's kind of where I head to. If I can shortcut something, I usually try to. So this is a nice shortcut. Any questions on this one? Okay. Oops. All right. Here's our last one for the day, and or for this section even. And I mentioned last time to you that for some reason, I don't know why, when I was planning this lesson, I really liked those tangent theta squared, right? The squared formulas for tangent. I don't know why, but it came up several times, didn't it? Do you guys remember us discussing that? And apparently I did it again because I see this happening again. So any ideas about what you might like to see happen on this one? Clearly the left-hand side is more complicated. Agreed? Mm-hmm. Yeah, so we probably want to work with that side of the equation to start with. So what do you think we might try?
Change the denominator to secant squared.
Okay, so use that tangent squared identity and involve secant squared in this. So the denominator would be secant squared. Sounds good. What are we going to do in the numerator? What's that?
Is it going to be negative?
Well, there's a relationship we can use, but it isn't quite that. See, we know that 1 plus tangent squared is secant squared, and this one's 1 minus tangent squared. So how about I do this? How about I write the 1 and the minus, and I replace tangent squared with something that's related to secant. So think about the identity that starts out 1 plus tangent squared equals secant squared. Okay, let's try that again. Secant squared. Pretend there's a theta over here. I can't get it in. It keeps changing slides on me. I'm sorry. How could I solve this for tangent? What would tangent squared actually equal? Secant squared minus 1. So could I replace the tangent squared in here with secant squared minus 1? I could, right? So I'm going to replace tangent with secant squared of theta minus 1. Why is it nice to get everything in terms of secants in this particular problem? Because they're the inverse, or the reciprocal is actually the word we want, right? They're the reciprocal of cosine, and the right-hand side's cosine, right? So it seems very reasonable to want to have those in terms of secant. Yes, Micaiah?
Why is it secant squared?
Because this formula right here on the right-hand side is that 1 plus tangent squared is secant squared. So if I subtracted the 1 to the other side, this equation would turn into tangent squared equals secant squared minus 1. Right, so this piece right here, just plain old tangent, is equal to secant squared minus 1. And we're using this formula right here to see that. Manipulate it a little bit. Agreed? All right, so I'm going to take what's in the numerator now, and I'm going to distribute the negative and see what happens. Okay, see if I can clean anything up, and hopefully I can. So this is now 1 minus secant squared theta, and then what? Plus 1 over secant squared of theta, and there's a plus 1 out here as well, isn't there? Okay, so I'm sorry? Because I've got a negative times a negative right here. Right, we're just distributing the negative through. Okay, is everybody okay to this point? What do you think I might try next? Okay, I can add the ones that are currently in the numerator. Sure, no problem. So this is going to be 2, whoops, let me use black. 2 minus secant squared theta plus 1 over secant squared theta. And I've still got the plus 1 on the outside that started there, right?
We shouldn't have that plus. Yeah.
Oh, you're right. I wrote it again, didn't I? How's that? Is that better? You bet. Sorry. Thank you, guys. Awesome. Is that all right? Okay, I'm going to copy this to the next screen so that we can keep working because I'm out of space. Okay, so this is where we're starting from. What could we do next, or what would you suggest? What would you like to see? Where the goal is, maybe I should copy that piece too.
Change them to cosine.
Whoops. Oh, I keep messing up. Sorry. One more time. Copy. There it is. This is my goal. Okay. Okay, and you mean this last one that we haven't dealt with here, right, Michael? Yeah. So what you don't see on the right-hand side of the equation is any addition of 1. Agreed? So I need to somehow combine the left-hand side so that there isn't any addition of 1. And the only way to combine those two pieces would be to get a common denominator to combine them. Make sense? So what would that fraction end up looking like right now to be helpful? Yeah. So I'm going to have the same one I had here, 2 minus secant squared theta over secant squared theta. And then I'm going to rewrite the number 1 as secant squared theta over secant squared theta. Right? And now that I have common denominators, I can combine the numerators. So my numerator, my entire numerator now is 2 minus secant squared theta plus secant squared theta, all over secant squared theta. Every step has to be equal to the step before. So you can't shortcut the system and just sort of ignore the denominator for the time being. Okay? You can ignore it in your mind, that's fine, but it has to be written on the paper because it has to be equal to the step before. But what beautiful thing happens now? You bet it does. These two add to 0, don't they? Which means I'm left with 2 over secant squared but what is something over secant squared the same as? That's the reciprocal of cosine, right? So this is the same as having 2 cosine squared theta, which is exactly what I wanted it to be to begin with. Right? Cosine is the same thing as 1 over secant. Well, that is 1 over secant. It's 2 over secant, so I can pull the 2 out, but it's over secant, so I can replace it in that way. Okay, so I know this is only the second time you've sort of seen this, at least in class with me. Is it starting to make some sense? Okay, so what we're going to do next is you're going to practice